Okay, guys. So now we're going to look at the notations, the standard notation and the scientific notation. We're going to look at some of the units and the prefixes. Then we're going to look at the significant figures and the rules regarding the rounding up and the rounding down. Okay, so first let's look at the notation. So anytime we are taking a data, we are logging our numbers. So you see the two numbers that are shown, one is a big number and the other is a small number. Okay, so in a standard notation, we write these numbers, and sometimes there could be lots of zeros depending upon how small the number is, or there could be a large number of digits depending upon how big the number is. So we need to condense it and write it in a scientific form, which takes in less space, and it just focuses on the most important digits in that number. So in this case, in the first case, as you see, it's 24,392, right? Now here, the decimal is implied. So we are going to move the decimal. So when you move the decimal 1, 2, 3, and 4. So we move the decimal to 4 places on the left-hand side. So when you move the decimal to the left side, and now the number becomes 2.4 into 10 to the power 4. Okay. On the other hand, when you have a very small number, and in that case, you're going to move the decimal 1, 2, 3, and 4. So in this case, we move the decimal 4 places. So as you can see, I'm moving it in between the zeros right here. Here also, I moved in between. So these spaces were counted. Okay, so now I moved the decimal to the right side. So here, what does the number become? It becomes 5.3 into 10 to the power negative 4. So for the small numbers, it's a negative exponent, but for a large number, it's a big exponent. It's a positive exponent. Okay. Next, we are going to look at the units. So these numbers by themselves don't mean anything. This number, 24,394, doesn't mean anything. Similarly, that small number doesn't mean anything. Even though you write it in scientific notation, basically, you're trying to, use less space on the paper in recording, okay? But those numbers don't mean anything until and unless we know in what context are we using them. So are we taking the measurements as regarding the length, or is it the amount of space an object is occupying, the measurements, the number is relevant to that? Or is this number signifying the mass or the weight of a substance? Or is it the temperature, the degree of like the heat that is present in the substance, or the substance is giving away the heat? So is that's temperature, right? Or what is the density? So those numbers have a value when we place a digit after that number. So these are some of the examples I've shown on the screen. So for the length, meters, millimeters, centimeters, kilometers, inches, yard, and feet, these are the units that are used to measure the length. Then comes the volume. Volumes is the amount of space an object occupied, and it can be measured in the units of length, liters, milliliters, quarts, centimeter cube, pint, gallons, and so forth. Okay, mass is the weight of an object, and so that can be measured in grams, milligrams, kilograms, micrograms, and tons. Okay, and the temperature, similarly, degree Celsius, degree Fahrenheit, or Kelvin. Density is derived from the formula. And again, there are two ways you can write the density. If we are looking at the liquids, then it's grams per milliliter. But if you're looking at solids, it's grams per centimeter cube. Okay, so these are the different units. Now let's look at these. So when we write the units, so if you've noticed it, millimeter, centimeter, kilometers, right? And here you have milli, and again, milligrams, kilograms, micrograms, right? So where is all that coming from? So these are the prefixes. Okay, so prefixes are, they give, like they signify whether a number is a big number or is it a small number. So this is again, this, it's kind of giving value to the units. Okay, so there are the larger numbers will be kilo, mega, giga, and tera. So as you've seen on the screen, kilo is anything that is raised to the power of 3. 10 raised to the power 3. Mega, 10 raised to the power 6. Giga, 10 to the power 9. And tera, 10 to the power 12. And peta, 10 to the power 15. So kilo can be kilograms. Kilo can be used as kilometers. Okay? Mega, like mega millions, okay, like gigabytes, terabytes, so this is what it means. Okay, then comes the prefixes that decrease in size, like deci. So it is going to be like, for example, deci liters, like smaller amount, right? Or decigram balance. Okay, so that's one thing. Now, centi is also like centimeters, right? And centimeters, centigrams balances, right? The ones that go as 2 places after the decimal. So this is going to be just 1 place after the decimal. This is 2 places after the decimal. Then comes the milli, like millimeters or milligrams. And that is, if you were to take the weights and you see those grams, those balances, the ones that have 3 digits after the decimal, they're a little bit more sensitive, more more exact. Then there is the micro, which is even smaller. So microgram, generally microliters, microgram. So in chemistry, generally we use these. Okay, nano is like really small, and pico is 10 to the power minus 12, nano 10 to the power 9, negative 9, and femto is really, really small, 10 to the power negative 15. Okay, so these are the prefixes that can be used with any one of these units as is needed, which signifies whether it's a bigger unit or a smaller unit. Okay. Next, commonly we see these equalities. Okay, these units now are used, generally the SI is a unit with a metric unit is like more common for the rest of the world, and US has a different system. So we need to equalize the metric and the US system whenever it's needed. So for that, you are going to refer to some of the tables. Either on the exams, these are going to be given to you, or you can use on the tables or simply do some Google search to find out one unit and the other unit, what is the equality of that. So for example, for the length, okay, so for the length, 1 kilometer is 1,000 meters, but 1 feet is equal to 12 inches. And so the relationship between inches and centimeters is 2.54 is equal to 1 inch. Okay, so we made these equalities so that we have the uniformity in the measurements, I mean, all over the world of whatever objects people are, dealing with. Okay, then comes the volume. 1 liter is 1,000 ml. So this is again commonly used, in chemistry, we commonly use these, and then so grams is grams and milligrams, and similarly liters and milliliters. So these conversions, commonly we use them. Okay, but we also see that liters and quarts are related. Okay, similarly quarts and pints, they are related. So these equalities are used to convert one unit to another unit, and the process that we use is, or the methodology that we use is the conversion factors, and we're going to deal with them later. But for now, just look at the significant figures. Now, since we are dealing with measurements, now somebody you know is going to determine what should be like the exactness, or in other words, okay, here's the thing, what I mean to say is that these measurements are done by different types of peoples, and these measurements are always in context. What, how many, there is going to be some accuracy we need, some precision we need in the measurement, and there can be some uncertainty which we can tolerate, okay, in the experiments or when we're doing these calculations. So, when we are taking this data, we measuring device, so you taking this, so there's little space in between the lines or even on the ruler, that is kind of ambiguous. So ambiguous is it's like there's no marking there. So we will have to just kind of guess. So there could be some, so how far can you go after the decimal, to determine that, to determine your uncertainty, in other words, okay? So significant figures, significant means important. What numbers are important in a measurement? Okay, so here's the thing. The number, a number, that number is a significant figure, or those numbers are a significant figures, and generally it relates to zeros. But let's look at it. Those numbers, significant figures means important, are counted. All the non-zero numbers are counted. Okay, so in other words, they are important or they are significant. Like for example, you have a number 2.3. So 2.3 does not have any zero. So this number will have two significant figures. Okay, similarly, if you have a number, for example, 1329.2 6. So in this case, the significant figures are 1, 2, 3, 4, 5, 6. So this comes out to be 6 significant figures. So I'm going to use SF for significant figures. Okay, so significant figures are, all of them are important numbers. So all non-zero numbers are counted. Simple. Next, look at the zero in between the non-zero digits. So the zero in between the non-zero digits, like for example, 304. So these are the two non-digits, and the zero is in between, so it has a value. So that means there are three significant figures. Okay, let us say you have another zero, another figure, which is like 4.002. So in this case, 4.002, in this number, there are four significant figures. So we are going to count 1, 2, 3, 4, all four of them. Okay, now zero, that is at the end of a decimal number. So that means, like, for example, 20 point. Okay, and again, these numbers right now, I'm not writing any units, but let us just assume this is 20 point liters. That means not less than 20, not more than 20. Okay, so it's not like 19.9 or 20.01 or 20.1. No, it's exact 20. The measurement should be exact 20. So in this case, the significant figures are going to be 2. So definitely we need 20. Okay. Similarly, if you have a zero, that is, so decimal numbers are like kind of, important. So for example, you have a number 32.0. Now 32.0, let us say this is 32.0 degrees Celsius. Sorry, 32.0 Celsius. So this is going to be 32.0. That means three significant figures. All the three are counted. So just because, decimal is there, it's that zero is important. Okay, like for example, you have 1, 5, 2.0, 0, and 0. So there are three zeros after the decimal. Okay, these three zeros after the decimal have a value. So this number is 1, 2, 3, 4, 5, 6. So there are 6 significant figures. Okay, so keep this in mind that anytime there is a decimal in the number, no matter where the zero is, it's always counted. Okay, next comes the zero in coefficient of a number in scientific notation. Like for example, you have a number, for example, like for example, 5.70 into 10 to the power -3. So In this case, again, it's a scientific notation. So suddenly this 10 doesn't count. You leave it. But these three are important. So these three are the three significant figures. Okay. Next is we are going to look at the zero is non-significant if it is. So in what cases is zero not important? The zero that is at the beginning of a decimal. So 0.0004. Let us say this is the number, and this is, let's say, this is 0.004 seconds. Okay, so in this case, how many significant figures? So these digits, these zeros are dropped. This, this, this zero, and this zero are not significant. So these are dropped. So the only zero that is left, the only figure that is important is one, and that is for one significant figure. So kind of like a little bit a little bit ambiguity here, because the same number can be written as a scientific notation, right? So in a way, those zeros are important because they help us to determine the scientific notation. However, just for the sake that those are not counted, in other words, you can say that. So that is just one significant figure. Okay, next is, let's look at another example of 0.075 centimeter. Okay, so here there's going to be, again, you're going to drop this, drop this, drop. And so when you drop this, then you're only left with two significant figures. Okay, now comes another very important concept of exact numbers. So what are exact numbers? Exact numbers are like 10, like 100, like 1,000, So all those, these numbers are, or even something like 1, 2, 5, 0, 0, 0, 0. Like I'm going to just put it here, right here. Okay, so that's a huge big number. Okay, so here, these are exact numbers. All of them are exact numbers. There's no decimal in the exact number. So anytime you have exact number, the significant figures, it will have variable significant figures. Or it's like it's infinite. Some of the books say infinite. So it doesn't matter if it's infinite or if it's variable significant figures. Means like they can be, it could be, in this case, it could be, in this case, it is, ideally, this is 1, this is 1, this is 1, this one can be 2, this could be 3, this could be 2, this could be 3, this could be 4. Okay, so in this case, again, 1, 2, 3, definitely 1, 2, 3 for sure. But you can write the answers in scientific notation. That is why the exact numbers, the significant figures, are kind of not given that much importance. So they are, because they are ambiguous. Okay, so in this case, they are variable significant figures, and like I'm saying, it depends what you are, in what context you are doing the measurement, and who needs that measurement, and for what purpose, those things. Okay, now we are going to look at the rules regarding rounding. So if the first digit to be dropped is 4 or less, okay, then the retained digit remains as is. So here's the rule of the thumb as far as chemistry goes. Do not round down, because we are dealing with matter. And if you're just estimating, it's okay to round down. But we prefer to keep things, otherwise you introduce ambiguity. So we prefer to keep things as far as possible. Even a little teeny little speck of a chemical can contain like thousands and thousands and thousands of molecules. So rounding down means that you are removed those molecules. So it doesn't make sense, right? So rounding down in chemistry is only for estimation purposes when you're just doing some mental math or something, but best is to just leave it as it is. Okay. So, and next thing is, anytime you're doing calculations, like all these different steps, you don't round up or down in between the steps, only the final answer. You can round up or, just leave it as it is. Don't round down. Okay. So here is it. If the first digit to be dropped is 5 or more, then in that case, the retained digit is increased by 1. So the retained digit is increased by 1. So here we see these two examples, and we want to have 3 examples, and we want to retain 3 significant figures. The answer needs 3 significant figures. And, that depends also why we need 3 significant figures, why we need 2 significant, why we need 1, why do we need certain places after the decimal. All those are the rules that relate to addition and subtraction and multiplication and division using the significant figures. So that later, but right now, so here we want to have 3 significant figures. That means we want this, we want this, and we want this. And these numbers are going to be dropped off. These will be dropped. So when these are dropped, then what should we do with 7? Okay, so 8 is being definite, and 2 and 3 are being dropped. But since 8 is more than 5, therefore our number now becomes 3, 5.8. Okay, and anytime you write the numbers, just make sure that you are also writing the units. Okay, so let us say, let's say this is, I don't know, this is grams. Let us say this is, 1 second. This is liters, let us say, and let us say this is also like grams. Okay, so this is 35.8, and this becomes grams. Okay, next is, let's say this again, you need 3 significant figures. So these are being dropped, definitely. We need to retain this, this, and this. And these, oh, sorry, wait a minute, my mistake here. I'm sorry. These will remain, but we are going to drop this and this. So drop these off. And so we see that 1 is less than 5, okay, or 4. So therefore, the number still becomes 0.0026 and 2. So 2 remains as it is, okay? Next is, you're going to look at this number in which we need to keep 3 significant figures, and we are dropping off 6, and 6 is more than 5. Therefore, 3.8, this becomes 3.83 into 10 to the power 3 grams. Okay, so 6 is more than 5, so 2 is raised 1 unit up. Okay, so this, we are going to stop here, and I hope it was easy, and thank you for watching.